We are recording. Welcome to the evening of Python coding. I'm pleased to present in this meetup uh, Deeksha and Yennam. I hope I didn't butcher the name. She will correct me. And she's going to talk about an NLP library that deals with translation. It has multiple names, but I'll let her explain the history about the name of and the acronyms behind. I think it's called MUSE, but she will explain exactly what it means, and she will show us what it can do. And Deeksha, go ahead. The floor is yours.
Thanks, Jacob. Can you all see my screen now?
Yes.
Hey everyone, my name is Deeksha Yennam. I'm a senior data scientist with Walmart Technology. I have a master's in business analytics from UT Austin. I graduated in 2018 and I've been working with Walmart since then as a data scientist. Today I'm going to talk about a multilingual embeddings model called MUSE. It's Multilingual Universal Sentence Encoder. I will dive into a little background about it and do a simple, very quick demo of what you can do with it. It's going to be very quick, but I'd like to encourage you all to ask any questions or interrupt me anytime you want. And if you want to follow along with the demo today, I have my notebook and a README documentation up on my GitHub. The link is here, and I think it was also in the event description for today if you go into the Python meetup link. If you all want some time to get started, I can wait or I can jump right in.
Go ahead. Go into
Sure.
this. They had the link for a while, and people can gonna come back to this. We're recording this, so
Okay.
go ahead.
Yeah. So just a little bit about what this encoder is. It's a pre-trained model that's available on TensorFlow Hub. It is an embedding model that converts text into a vector representation. I'm not sure how many of you are familiar with embeddings or have used embeddings in the past, but embeddings are a way to represent text in terms of numbers. So think of it as most often we hear about word to vec or doc to vec, where it uh, these are models that represent words or text as numbers, and we train these models on very large data sets to learn representations, in the sense that you learn which words occur together, and based on that, similar words that appear in similar contexts will lie in the similar spaces when you represent them as vectors. So this multilingual universal sentence encoder is a model by Google that was released, I think, early or late 2019, if I'm not wrong, or early 2019. Um, this converts any text, not just words or sentence level. If you have paragraphs, you can basically pass the entire paragraph as an input to this model, and it will output a 512 dimension vector that represents the context of the text that you're inputting into it. This model is a pre-trained model. As I said before, it just means that it was the weights of the neural network were trained on a large data set. And also it was trained to perform well on multiple natural language processing tasks like document classification, translation, and things like that. And so you can use this model as a module without having to train any new model or anything. It's just a pre-trained model that you download onto your system, and then you pass in any text that you have, and it outputs this 512 dimension vector. We'll go in a little deeper into what you can do with these vectors and the power of embeddings in general. And the there's lots of embedding models out there. The salient feature for this model is that it's a multilingual model. So that means it's actually language agnostic. It works with 16 different languages. And the best part is you do not have to specify which language your input text is in. So if you have a mix of, say, English, Spanish, and French, and something else in your data set, you don't have to tell the model which languages you are passing in as an input. It automatically gives vector representations appropriate without having to know which language the text is in. And then yeah, that's the salient features. And as I said before, it works for multi-word text, so sentences or short paragraphs, emails, things like that. It works perfectly fine. I have even tried to use it on longer documents with multiple pages, but then at that point it becomes slightly less performant. And how to use it: this is a pre-trained model. As I said before, it is available on TensorFlow Hub. If you have never checked out TensorFlow Hub before, I would recommend going to tfhub.dev. And this is a page that has a lot of pre-trained models by Google available as downloadable modules that you can use on TensorFlow. As you can see Universal Sentence Encoder Large, Multilingual, and so on. And there's a ton of other different NLP models, as well as some image classification and image recognition models as well. So you can check these out. And Universal Sentence Encoder is a family of models. Initially, they first released the Universal Sentence Encoder, which was just trained on English. And then in subsequent releases, they also released like the multilingual version of that model that works with different languages, which is what we are going to look into today. How to use it? Well, yeah, you download the model from TF Hub, and I'll show you a simple demo of how to apply it on a set of sentences. But there are multiple examples on TensorFlow documentation as well, if you want to dive deeper into its applications in NLP. The limitations of this model in particular is pretty large. It has about, I think, 70 million parameters or something like that in the neural network, and so it's about 500 megabyte size. It takes a while to download the first time, but then you can cache it into your system, and then you don't have to download it again. Or and the other thing is, if you're running it on a very large data set, like millions of rows, then you'd want to be more cognizant of what kind of computational resources you have, and also using the tf.data dataset input pipeline from TensorFlow that kind of optimizes these into batches for processing. And then I've included some resources here if you want to explore more about the model in general, or if you want to read the actual paper that was published by Google, it's right here. And yeah, then we can jump into the demo unless anyone has any questions so far.
I saw Silas is having problem with installing the notebook. Do you have?
Well, no. I installed the notebook, and the notebook loaded fine. But when I ran that second step, it bottomed out with that error that I posted there. I'm not sure if we'll have time to dig into it. You can.
Yeah, but Deeksha, what libraries or what environment usually you set up when you use this? Like.
So it's already here in the requirements.txt.
Yeah, I followed
you need a lot more than like TensorFlow, TensorFlow Hub, and TensorFlow Text. But yeah, I agree. This module sometimes can give you like really weird errors. It's pretty specific about like the version of TensorFlow you use and your operating system and things like that. So we can dig into that error a little bit later if that's okay.
All right.
It's no problem. We can fix this. I just wanted to know whether there's something specific, like it works on like only a specific Linux operating system or something like this. So this is what I was asking. Like,
So I use it on my Mac and it works fine. I don't have experience with Windows or other systems.
This is a Mac too.
Yeah. Can you quickly tell me what the error is? I'm not able to see my chat.
We'll treat this later. Just continue.
Okay.
Continue. This is not that important. I believe it's working. So the question is how to set it up. If you had some special magic sauce, that's the only thing. It's fine.
Sure.
Continue.
Okay. And so I just wanted to first demo it with like a set of English sentences. I just took a couple of examples, like I have a dog, I would love to have a pet, and I live in a big city. Just looking at these three sentences, if I were to think about the similarity between these sentences, I would think that the first two sentences are somewhat related to each other, and they are not as much related to the third sentence. So I would expect that if I calculated like the cosine similarity between these sentences, the first two would have higher similarity to each other, whereas they'd have lower similarity to the third one. And that's what I want to quickly demo.
Tell people what cosine similarity is. Some of them know it, some of them don't. So please tell it in a few words.
Sure. Cosine similarity is just a way to measure the similarity between sentences. And so, for example, because we will be representing these as vectors, if you were to represent these sentences on a coordinate space, you could imagine that the angle between these two, the vectors that represent two sentences, would be a kind of an indicator for how similar or how close to each other they lie on the vector space, and that's what cosine similarity is. So here we'll be doing a simple dot product of the two vectors, and since the model outputs normalized vectors, so a bar dot b bar is mod a mod b cos theta, right? So the cosine similarity will be the same as the dot product here, since they're normalized vectors. That's about it. It's just a way to numerically represent the similarity between sentences. If you want more information about it, you can look it up. There are more traditional ways of doing cosine similarity than using embeddings. So yeah, the first step, I'm just importing the libraries that I need. TensorFlow Hub is the module that I will be using, the library I will be using to load my module. I need NLP NumPy to do the dot product, and then TensorFlow Text is just another library that's used by the MUSE model to do the sentence pre-processing before it outputs your embeddings. So unlike other NLP libraries, you don't generally have to do any pre-processing before you put your text into this model, because it already has a pre-processing module built into it that takes care of some standard pre-processing steps, like removing the stop words or removing punctuations or new lines or things like that. I don't bother doing any of that when I'm using this. I just, whatever document or text I have, I just input it into the model. So now you're going to load the model. Here I'm loading the model using, this is the module URL. This is, by the way, general for any TF Hub module that you use. You specify the URL of the model that you're using, and then you use the hub.load functionality to load in your model. And so I'm loading the model, I'm calling it embed, and then all I'm doing is I had the sentences as a list, and I'm going to pass that list to the embed function, and that will return a list of, or a tensor of embeddings for me. So I passed in 3 sentences as a list, and I've got a tensor of shape 3 by 512. So each sentence has been converted into vector of dimension 512. And now I'm going to calculate the similarity between these sentences using a dot product. So here I'm doing a dot product of pairs of sentences, 0, 1. So the first two sentences, and then 1 and 2, and then 0 and 2. And you can see the similarity scores between each of these. As expected, the similarity score between the first two sentences is a lot higher than the other pairs of sentences. So this is fine. It works for English, but the model is multilingual universal sentence encoder, right? So I want to give you a brief demo of how it works with multilingual data. And so what I did is I took these sentences and I put them into Google Translate and I converted them into different languages. So I have a dog into Spanish, the second sentence into French, and the third sentence is in, I think, Italian. So I just randomly chose 3 languages I wanted to test this out in and converted into those languages. And now I'm doing the same thing as I did before. I'm just embedding these sentences and calling that embeddings _2. As you can see, I have not specified what language these sentences are in. I have not given any information about, whether these sentences are English, non-English, anything like that to the model. Now I'm going to do the same thing that I did before and calculate the similarity scores. The first thing I'm going to do is calculate the similarity scores of the English sentence with its exact translation into a different language and see how that score is. So if you see here, I have a dog and its direct translation into Spanish. Based on the model embeddings that this model gave me, the similarity score comes out to 0.92, which is pretty great. So like I have not told the model anything about the languages or anything, but just the embeddings when they come out of the model are so close together in that 512 dimension space that when I do the dot product, they are highly similar to each other. And same thing with the other sentences and their direct translations into different languages. You can see that the similarity scores are very high. An application of this would be in, for example, in the evaluation of this model, what they did was there's this evaluation task where you're given a sentence in English, and then there are 5 different options of its translation into a language. And they compared how this model performs on that data set, and it did really well. If you want to see more about the performance of this model on different the metrics and on different data set, like benchmark tasks, you can go directly to the URL, and they have listed all of the performances here. The next thing I did was compare the similarity scores between the sentence in English and say another sentence in another language, and I just wanted to see how it performs. So the similarity score we saw between these 2 sentences was pretty high, 0.6 in English. But when I do the same thing in a different language, it's the same sentence as I would love to have a pet. It's just that this is in French, and the score is 0.57. Pretty close to 0.6. And also if I did the same thing in Spanish and French, and it's 0.56 again. So this is my demo. I just wanted to give you a very brief introduction into what this model is and what its capability is. But in general, when you're using embeddings, this is probably not like the practical way you're going to use it. You probably want to use it in a document classification task, or some or a semantic similarity. This is a semantic similarity task, but you can also do in terms of like a semantic retrieval, where in your database you have multiple documents in different languages, and given a document you want to retrieve similar documents to that document, kind of like a very smart search, and you can imagine converting all of those documents into these 512 dimension vector spaces, and whenever someone is looking for a document that's similar to one that they already have, then it's as simple as fetching all the documents that are closest to the document of interest. And it can be so powerful because it doesn't have to be in the same language or anything like that at all. It can be in multiple languages, especially like if you work in a very big corporate company with operations in multiple countries. You can imagine how you might have access to a lot of documents that are in different languages. Especially the most common I found is English and Spanish seem to be the most common, because even within the US, Spanish is used quite often in official communications. So that was my demo, and if you want to look into more about how to apply embeddings in classification or any other NLP tasks, TensorFlow has a ton of examples. This is one example that I just pulled up. It's text classification with movie reviews. It uses an embeddings model, which is slightly different from what I used, but again, it's the same thing as instead of this, if you were to use the MUSE URL and uh, did everything else the same, it would still work. So it's just I think if you followed this example, it would give you a more realistic view into how you could use multilingual embeddings for document classification. And that's all I had for today. So I can start taking any questions now.
I have one question.
Sure.
So I've used NLP in the past, and I know that you can build these models based on either a character, like on a character by character basis, or on a word by word basis. Do you know if there is any difficulty in any particular language building with words or building with characters? Is one advantageous over the other for certain languages?
I don't know, depending on language, but in general, I found that fast text is a model that goes by n-grams instead of words as a whole when calculating embeddings, and I find that really powerful. And you can imagine using those in different applications other than even in the traditional sense of a word. If you had, say, DNS names or anything like that in your data set, which has some structure to it, but it's not necessarily words, then character level embeddings can be really useful. Whereas word to vec and things like that or on pre-trained word embeddings with limited vocabulary, they are still good because they're very simple, and for your normal day-to-day NLP applications, they should do well.
All right, thank you.
You use the term n-grams. Some of the people here don't know n-grams, what n-grams are. So please explain just n-grams, but I have a question afterwards.
Yeah, so n-grams are just groupings of characters in a word. So for example, if I had the word Python, say, and if I were to look for n is like the number, so it can be 3 grams, 4 grams, 2 grams, whatever, bigrams, trigrams, things like that. So if I were to do trigrams, I could do PYT, YTH, THO, and so on. So when you're using n-grams as a way to do word embeddings, you can imagine a situation where someone probably had a misspelling of Python, and they did PYTHO T instead of N. But then when you're doing these n-grams, since you're considering like, three in batches of 3 characters, even though the last character is wrong, your model will still recognize that it seems to be very close to a word that I already have in my vocabulary. And so, that helps you avoid some issues, especially when it is informal text, either, typed out by someone or something like that. So that's the concept. Look up fast text embeddings if you're interested in some application like that. I found it really useful. It's by Facebook.
Oh, thank you. Now, MUSE, you showed an example using MUSE where you actually just convert sentences into numbers. So, for people who don't know the power of embeddings, can you explain a bit more? Some of the people here don't understand because they're not from the field, and some already know this. But can you explain why those vectors and what you can do with those vectors only as vectors? This is one thing, and then the question is, what is the next? The second question is, what is the next step of things you can do other than just finding similarities? So
Yeah, sure. Embeddings in general, as I explained before, it is a way to represent your words or text in numbers, because in normal data science applications, when you talk about different tasks, almost always your feature set is a set of numbers, right? And how would you do that when you have text? How would you do use a logistic regression or an SVM on text, right? So that's where the whole idea starts. And one of the most easy ways to do it is through this concept called TF-IDF, where you look at, how many times is this word occurring in my document, how many times is it occurring in the whole corpus, and use that as a metric to determine, what is like the importance of the word and things like that. But then we have then we got this concept of word embeddings, where you given a corpus, you are looking at each word and saying, how can I predict the words that are occurring around this word most often? So you start to construct a probability, a model that predicts the probability for a context word appearing in the vicinity of a given word. And so that's the concept of word vectors. And eventually you learn a neural network that will output for each word in your vocabulary a vector of, let's say, 300 that is representational of the vector space in which this word would lie, had when you learn this probabilities. So that's the concept of word vectors. We have a lot of pre-trained word vectors available. For example, word2vec. You have this model that's trained on the entire Wikipedia corpus or the entire Google News Group's Google News data. And so you can imagine like that would be a very huge corpus to learn what words occur together in general in English language, things like that. So that you would imagine that when you use those pre-trained vectors into your own data set, it would still, those concepts would still apply. And so those would translate into your whatever NLP task you are looking at. So that's the concept of word embeddings. If you want to look up more about word embeddings, there is give me a second. There should be this is a resource on TensorFlow about word embeddings and the whole concept, which is pretty cool. And there are plenty of Medium articles and so on that will do a great introduction into word embeddings. What we looked at today is not word embeddings, but it's actually sentence encoding. So it's not just taking a word and converting it into a vector. It's converting a whole sentence or a blob of text into one vector. And the second part of your question, Jacob, was about where else you can use this, right? Like I mentioned before, you can use this in document classification, in semantic retrieval, in sentiment analysis as well. So multiple different applications. Once you have converted your text into a vector, then you can imagine, like, any of the data science tasks that you would do with normal numerical features, you would be able to do with your text.
Hi, Deeksha. I'm Sheetal. I'm a recent graduate from the UT Data Science Bootcamp, and for my capstone project, my last project, I built a beer recommender using a machine learning model. And I'm currently trying to expand that model using NLP based, I have a big data set of a lot of reviews. So the reviews currently are primarily in English, but then if in case I expand my data set to a data which has multilingual reviews, can this be incorporated or made it in? Can it be pipelined, or also how easy it is to deploy this particular
Yeah.
technology?
Yeah, definitely. I think that would be like a perfect use case of when you would use multilingual embeddings, primarily because you don't have to translate whatever data you have into English before using your model, or even specifying which language your reviews are in. As long as they are short paragraphs, or even slightly longer will do. You can use the MUSE embeddings. So as far as deployment, it really depends on the size of your dataset. If it's small enough, if it's really small, like for any of your like within, like 10,000 emails, sorry, 10,000 documents or something like that, then you can definitely directly just use pass those in as sentences, and do it on your like personal computer very easily. But as you start going into bigger data sets, you will have to, that's what I said, it is a large model, so you need to be um, so TensorFlow has a pipeline, input data pipeline called tf.data. You can use that as a way to batch your inputs into the model, so it does batch wise at a time. So you'll require much less computation time doing that. And if it gets into millions, you'll probably need a GPU, which is what I had to do in one of my applications.
Oh, thank you.
You're getting compliments here from the people who don't unmute themselves, but they like the presentation. So this is good. I have another question about do you know any information about how this model has been trained? Like each character is trained separately, each word there? Like, because you're doing sentence embedding here. What's
Yeah.
like the small atomic element there?
Sure. So, as I said before, this model is a part of a larger like family of models that Google released. The one that I am using is a moderately sized model, but they also have a larger version of this model that uses a different architecture. The architecture for the model that I am using is a convolutional neural network. It's a CNN. So what they do is as you pass in the sentence or paragraph, it breaks it tokenizes your text into words, and then each word is assigned an embedding from a pre-trained set like word2vec or some other embedding they may be using. Those embeddings are then passed into the CNN, and they get converted at the end of the deep network into this 512 dimension embedding. And then the way they train this encoder is by training this on multiple different NLP tasks. So they used, so they have this encoder whose output they're going to feed into different NLP tasks, like, sentence classification. And because it's multilingual, they used a ton of different sentence translation tasks, and so on, and trained the model to perform well on all of those different tasks. And the weights that they learned on these different tasks are what are saved in your pre-trained model that you are downloading from TF-Hub. And also, if you want to fine-tune this network to, say, they may have used it on Google News or something like that, or some standard tasks, right? And you have some other data set that probably has a little more nuance to the language in it. You can certainly fine tune this embeddings to fit to your data set. You just have to, when you load this embeddings as a layer in your Keras layer, you just need to say trainable equal to true, and that will set all the weights of the neural network to be trainable for the task that you are working on. So that way you can fine tune this model to work better with your data sets. Although I would only do that if I had some specific requirement to do so. Otherwise, and it will be computationally expensive as well, because it's a very deep network. Yeah, that's about it. And I also would want to address the error that you're seeing, the one where it says symbol not found, check stack Darwin. I actually saw this error recently, and see where it says in the brackets, which was built for Mac OS X 10.15. I think that's the Catalina OS. So if you have Mac OS, if you have upgraded to Mac OS Catalina, that error should go away. If you have a previous OS, I think that error is coming from because of your OS. Does that help?
Silas, this was your error.
Sorry.
Yeah.
Still here.
Yeah,
I'm here.
Yeah.
Sorry, talking about your error.
Well, I just want to know if anybody else recognizes it. I'm not sure how much we can do.
Yeah, I was just talking about that. So that is, it should go away if you upgrade your Mac OS to Catalina. So in the bracket it says which was built for Mac OS X 10.15. You can see that's Catalina.
Gotcha.
So if you have Catalina, that should go away. I don't know why that's happening. It's a recent error, but that's from TensorFlow text module, from what I can see.
Okay, good.
Good. So we solved that problem. I have one more question. Unless someone else wants to ask more questions. Anyone else wants to ask questions, or okay? You think about questions, and I'll ask mine. This is a multilingual library. What you have here, multilingual solution here. It has some level of translation, because you showed examples where you actually take sentences and compare them, and then the system tells you, oh, I recognize those are similar.
Mm-hmm.
Now, I have a question. If you want to actually use this, is this library actually useful for direct translation, or are there other tools to use for direct translation?
I think for you would use other models, like you'd need a sequence to sequence model to do that, right? So you have like a sentence, and then your model needs to predict what word comes one after the other, like when it turns it into a sentence in a different language. So you would need something else. So right now you have like the only encoder portion of your sequence to sequence model, so to say. So if you had like an encoder plus a decoder, then you would be able to do that translation directly. But what you can do here, and what they have done as part of an evaluation for this model, is say you have a sentence and you have like different options in in another language for which one is closest to the sentence you have in English, then you can definitely use this model.
Well, thank you. This is a good explanation of what it can do and what other things can be done using it. Thank you. This is really good. If anyone has more questions, now is the time. Questions going once, questions going twice. Oh, okay, there's a question. How does a model handle, wait a second, I have to read it. How does a model handle words with smaller meanings like hello versus hi?
Yeah, as I said, here embeddings in general by what words occur in the same context or what words occur in close proximity to each other in text. So hello and hi, I would, if we were to put this into the model, it would have very high correlation to each other. So yeah, that's the whole concept of embeddings. It's not about what words are exactly similar, exact translations or exact synonyms. It's about how do words appear in the context of each other in language, and how can we represent them as text, as numbers.
Okay, we have an answer here. So again, more questions going once, more questions going twice. Well, more questions going third time. I see no one has more questions. So, Deeksha, I want to thank you on behalf of everyone here. If everyone would unmute themselves, if whatever they can, and give Deeksha a nice clap, it would be nice. And I see Sherry. We're gonna stop the recording, but please stick around. We have